Hey everyone, welcome to Office Hours. It's the day after the test. Good to see you here. If you're here in the chat, we'll start off with a little 320, show some cool stuff. So let's go here to 53 and BS 320 influence plots. So here we go. Let's check it out. So what's really interesting is a lot of times people talk about with regression, like what points are outliers, what points are influential. And we can actually figure that out. So if you just took the 201 test, maybe you're watching this, people say, well, when is it an outlier? And we actually have really good ways of analyzing this. So this is regression inside of R right here. And what we're doing is we're making a model to explain somebody's height with their weight. So let's show what this kind of looks like right here. We're just going to visualize it easily with this. This is a very quick way to visualize models. And you can see right here, we're using weight as the X variable and height as the Y variable. Now you'll notice you have like this point way up here, these 3 points down here, 1, 2, 3 over here, and then these kind of cluster of 3 down here. So a lot of times what we like to do, and we'll keep this graphic kind of over to the side, is we like to show and plot on these things, like draw on them is what I'm about to do when we get a nice perfect picture out here. I like to talk about these things and point out odd things. So we've got one extreme point over there, got a cluster of 3 down here, and then these kind of cluster of 3s. These are actually 95% conf intervals. These right here are 95% prediction intervals, I should say, for individuals. And this is the 95% conf interval for the middle line. Same thing goes for the other side of it right there, and the 95% prediction interval for individual points. Prediction intervals are what we use to predict an individual's height, where confidence intervals are for the middle line. So those are not going to be important in the additional analysis we're going to do. Just wanted to point out what those are. And you can see the outliers-ish, those are kind of extreme values, are far away from the line itself. Now we have additional ways of doing this, and we have additional diagnostics. So there's some values I've listed right here. And the values I've listed are what's called Cook's distance, the Hatz values. Cook's, yeah. So many values. And there is no leverage. I think I ran this and someone said, wait, there is no leverage. We actually want this value right here. That's why. Someone emailed me about that or message on Discord. So let's start here with the first thing, Cook's distance. Cook's distance, this value right here, is a metric of the influence a point has on a model. So if you were to look at the Cook's distance right here, things with higher Cook's distance and they're large numbers, basically is how much influence on the model. Larger values mean more influence. More influence means it's pulling it in a bigger direction. That's probably the most influential point. More on in a moment, but it's the furthest away from the model. It's probably going to pull the model towards it because we don't like outliers. They heavily influence the model. And we can actually measure this. You can literally, you can do which.max and find out which of these is the maximum Cook's distance. I don't know why it's reporting it twice for me right there. Oh, because it's row 251 and it's 251. So it is row 251, and we'll see more on that here in a moment, but that seems to probably that one right there. And what I could do if I want is I could go ahead and actually look at that, and we could confirm it's that individual. Go to survey 10 here, go to row 251. We're only going to look at the height and weight of the individual. I wrote some code for this yesterday, and that person is 260 pounds, and look right there, 260, 54 inches. So my suspicions were correct that they are the most influential point in the model. Just kind of knowing what I know, that you have to be pretty far away, and then you also have to be far away from the model. So far away on the X's, and then far away from the model itself. Next, we have the Hatz values right here, and Hatz is actually leverage. So leverage is how far is a point away from the mean of the X's. So when you look at the mean of the X's right here on leverage, there's only one X in this model, so it's easier to compute which point is the furthest away. The mean of the X's might be about here at about, let's say, 160-ish. It's a good guesstimate. So it's either going to be this point over here or this point over here. Reason being is leverage is the distance it is away from the mean of the X's, and it's probably going to be that person who's like 305 pounds. So when we go to the Hatz right here, it'll compute a value for leverage for how far something is away from the mean of the X's. And if we go here and write the same code with which.max, and then we go to the Hatz values, it's going to probably be that person right there, 428. So we're going to use the same code right here just to learn a little bit about that person. And that person is 78 inches tall and 305. We were correct. Now, this person is not an outlier because they are right on the model. The model is the red line. So that person is right there where we would predict them to be. So nothing is unusual about that person other than they have they have a high height, they have a high weight, but in the bivariate sense, they follow the model. So that's that individual right there we're looking at. Now, the R student is basically the residual. So the residual right here is actually done a little bit differently. This is what's called a deleted studentized residual. And I think we have the notes still open from yesterday, which is going to be a huge help for kind of talking about this concept. When we do residuals, a residual is how far is the point away from the line. But when we do a deleted residual, we delete the point and make the line without it, because the point will influence the line towards it. So a deleted residual removes the influence of the point. So we remove the point's influence and we'd get a new line without the point. So that's why it's called deleted. So there's the deleted residual, or the deleted new line now. And then we calculate the residual to the line without the point's influence. Hence, we call it a deleted residual. Now, we also say it's studentized, which basically means standardized. And this is where your Stat 201 knowledge comes into play, because you'll notice on these plots, I've drawn on a ton of them right now. You'll notice on these plots, we're going plus or minus 2, and it's basically z-scores. Now, it's a t-score right there, but basically plus or minus 2 because we expect 95% of deleted. And it's basically standardized, basically z-scores. T's are basically z's. You'll hear me say that as we go towards test 3. So 95% would be expected to be between there. And if you notice, very few are outside these bounds right here. And that's why I have the below and above drawn right here. So you notice very few are outside of here and very few are outside of here if you look below this and if you look above this for points. So we did a lot of these plots yesterday to try to understand them and to understand these concepts right here. So now that we know the values we are calculating, hey, Jackson, good to see you here. Ask questions if you got it. Mewbot's in the chat. I'll throw 100 points right there. I'm going to re-wake up Mewbot. But ask questions if you got it, Jackson. I'm just chilling here talking a little bit about 320 for the moment. But drop those questions in the chat. We're re-waking up Mewbot. So we can actually make that influence plot super easily, but I'm going to make it even better. The influence plot right here. These are the influential points. The larger the circle, that is the size of the influence we calculated. The leverage down here on the bottom is the Hatz calculation, and the deleted studentized residuals. So here I'll literally highlight them again as we talk about it. The Cook's distance right here that we calculated, that gives you the size of the circle. So that's the most influential point. These are super duper not influential, those little tiny specks right there. Next, we have the Hatz value, which is going to be the amount of leverage. Now be careful, something with 0 leverage would actually be at the mean of the line, of the mean of the X values right here. So this is no leverage. Higher leverage is further out over here. This is high leverage, and this is high leverage. Leverage only deals with the X's and how far something is away from the X's. And then the last thing we have right here is the R student value, and that is on the Y-axis right here, which is a deleted studentized residual, which we just talked about a moment ago. So we made this plot right here, and it's kind of nice, but preferably we made some really cool plots at the very, very end of class. We went a little bit further, and we made the following plot, and it's all mad at me. Warning. It says, can't do it. Wouldn't be prudent. Here we go. There's a plot we made at the very end right here, and we like to make plots that really allow us to interact with the data. So this is our ggplotly object. Which we can now actually just turn off the non-influential points and focus in on just these and actually see those values we calculated. So what's really neat about this is if you look at this point right here, you can actually see its influence is 0.2452, and this one has an influence of 0.026. So this point right here is actually about 10 times, if you look at the ratio 0.02, 0.2, it's almost 10 times more influential. So this is a super duper influential point. This one is the second most influential. And also you can note, yeah, here, Jackson, let's take a look at that. We'll take a look at that next. You got it. You can take a look at this point over here, which was not marked as influential because it didn't have enough leverage, but you can see that it has an influence of 0.06, where this one has an influence of 0.0587. So it's actually a close call. It's just that this one barely didn't have enough leverage. It needs to be in this top quadrant or this bottom quadrant, which would mean it would have enough leverage, and it would have enough leverage, be to the right, and have enough deleted studentized residual to be in these quadrants over here. So this plot is really going to, I think, is a great way to display it. You can take a screenshot of it. There's ways to save it on here. Just going to save that image right there. And great stuff. Here we'll do, could you give an example again where would be full credit on the interpretation questions regarding slope or R squared? Yeah. So take a look at what we have right here. We have a model predicting somebody's. So what would you say? This is a model predicting somebody's height from their weight. So how would you interpret the R squared right here? So Jackson, what would you say? This is a model predicting somebody's height from their weight. How would you interpret the R squared right there? How would you interpret? What would you say, Jackson? What would you say? It's a good question right here. We'll put a little music. How would we interpret the R squared right there? Regression is super important. It's one of the most basic stats techniques we have. It's a little advanced, but it's like the basic advanced technique. It's used a lot. So there's the value of R squared. So how would we interpret the R squared for this regression right here with height and weight? And it's really good to practice seeing other output because you don't always see the same jump output, but this looks very similar to jump output. I think we have a jump output over here. If you notice, you do get the same sort of output with the R squared value, the intercept, the X right there. And there's the intercept, the X, the estimate, the standard error, the T, and the P value. So how do we interpret this R squared right here? Give it another good 30 seconds right here. What do you say, Jackson? How would we interpret that R squared? So we say, I'll start the explanation out. We say blank percent of the, what do we say? Good practice right here to get it down. Have your notes out, take a look, remember to fill in the blanks. So we would say, so remember, so R squared is going to be the percent of variation Y explained by the variation in X. So remember, and definitely check us out. So one of the big things here is one of my biggest suggestions is a lot of times for the interpretations on the test, the best thing to do. Were you able to check out the Kahoot review? With the Kahoot review, we went over the interpretations right in here. Here's us doing the interpretations. And R squared was last. Here we go. So here is the R squared interpretation on the screen. Blank percent of the variation Y is explained by the variation in X. So that's the interpretation. So how would we interpret this now if this is the R squared? So there it is right there. There's the interpretation. So how would we do that now, Jackson? 100 points. Keep practicing right here. How would we do this now? So there's the R squared value. We can see the Y and we can see the X. So what would we say here? What will we say here? There's the R squared value. There's the Y. There's the X. So we just want to plug in the R squared, but it's times it by 100, which make sure it times it by 100 because it's a percent of variation explained. 36.13% of the variation height is explained with, yay, Jackson, great job right there. Excellent work. That's exactly it. Yep, that's how to do it. Just plug it in, practice, and then write it down. The more you write these things down, there'll be interpretations on test 3. I'll do the same sort of thing for test 3. Test 3 is a little bit longer on the interpretations, but we'll learn how to do them. And just the more you practice it, the better you get at it. And you just have to be able to be like, okay, I can write this interpretation each time. And you said you wanted to do the slope also, right? So let's bring up the slope note interpretation right here. That's the intercept. So I think slope I did second. That's intercept. Intercept. Was slope third? Slope might have been first. There it is. So there's the slope interpretation. Yeah, no worries. It's about practice. Jackson, thank you for being here. All right, so there is the slope interpretation. Do I disappear off the screen? No. To increase slope, we have to do. Here's the slope interpretation. For each 1 unit increase in X, we expect Y to increase or decrease. Like you have to pick one of these. I underline them for a reason by B1 on average. Okay, so let's look over here at our data. You ready? What is the coefficient of the slope? I think we were a little bit nicer on the test. We just kind of gave you the equation, but can you tell from this output right here, what is the slope? Like right now you can just type, what is the slope? Like the number of the slope. So like what just is the value of the slope? Which we were nicer on the test. We I don't think like there's a way in here like to be like you can do coefficients. It'll tell you the coefficient of the model. There's the coefficients. 0.07 exactly, and you see it right there. So it literally tells you if you say coefficients, you can do coefficients also. Yeah, same code apparently. So that's the coefficient of weight, which is the coefficient of the x variable. And so now think about this. How would you then interpret this right here for each 1 unit increase in x? So we have to change that to whatever the context is. We expect y, with the context there, to increase or decrease. We'll know whether slope is positive or negative by b1 on average. So have this written down. Try filling it out right here. And what would you fill out right there? What would you write? This is the good practice right here. Remember this for test 3. And Jackson, thank you so much for being here. Jackson, we're throwing you 500 points just for being here today. And I really appreciate when people ask, like, well, how could I do this better? And 500 points just for being here, Jackson. You might be the only one here right now, but really good review, really good practice. Remember those mu bucks add up. You can get up to 1.3 points on your final grade. And this is just good practice, Jackson. So thank you for being here. Remember for test 3, there will be more written interpretations. The more you practice them, the more you write them down, you get to the test and you say, I know how to do this. And then we also want to understand them conceptually speaking, like know in the output where to find the estimate of the slope, know that the p-value is the significance of the model. We get into more of these other values in 320, like this is the uncertainty and this is the ratio of the estimate to the uncertainty. This is a typical miss the model makes. Degrees of freedom are used for calculation purposes. This is the R squared after a penalty term. And yeah, we actually just no, we got those open from yesterday. We talked about R squared adjusted in the 320 class. It's a very simple concept. It's literally R squared with a penalty term, so it can be negative. And then we mentioned the key things right here. So that's R squared adjusted, which is in that output, which is also in output right here. Notice how it's negative because it's R squared with a penalty term. So how would we interpret the slope coefficient? For each 1 unit increase in x, we expect y to increase or decrease. For each 1 unit increase in weight, we expect height to increase by 0.07. And then they should give you that. Usually a lot of times we give you the units in the problem. Jackson, another 100 points. Great answer right there. Graders might give that a 3.5. They could give it a 4. There is variation from graders. If you think the grader was unfair to you, let me know. That is great answer right there. I might say for each additional pound somebody weighs, we would expect their height. We expect their height to increase by 0.07 inches on average. Exactly, weight in pounds and inches. And then the question would probably give you that context. And if you looking at the scale of this does look like inches. This does look like pounds. And usually the question gives context. Yeah, we would usually try to give you that context, and then you would add in whatever context. But like if a grader give that 3.5, I'd be okay. If a grader give that 4, I'd be okay. If they give it like a 3, I'd probably be like, nah, that's pretty much what we're looking for. Like that's a 3.5 or 4 answer. But then a lot of times we sure it up by giving it a little more context. Does that make sense, Jackson? Like variation in grading, some grader might be like, well, you should add in pounds and inches. And I'd be like, well, yeah, they're kind of right. We should add in the pounds and inches, but it's not like wrong in any way. It's just we could be more precise. And 3.5 out of 4 is not bad. That's a 87.5 on that question. But if I don't know, I'd look over it and I'd look over how everyone was graded. But Terry's really great on getting all the graders on track. So usually I just make sure they're consistent across students. And then if they're consistent, then that's good. Hi, is this? Oh, no, this is not a good question, Taylor, right there. It's not data. Are you wondering about Data Analytics 6? I think that's we could start. When does that due? When is Data Analytics 6 due? We could talk about that. When is Data Analytics 6 due? I think that's the short one, right? Or the writing the responses one. Is that coming up here? I mean, it is coming up, obviously. Data Analytics 6 is due Wednesday next week. Executive Summary and Future Research. I need to include the videos on this. I need to put the videos at the top of this, like video at the top. You want to talk about Data Analytics 6? Next week. I know, right? Coming up so quickly. So we'll talk about Data Analytics 6. Let's switch topics here. Data Analytics 6. Yay, let's do it. Okay, 2213. Stat 201. Data Analytics 6. Okay. The first thing you need to know is look at the what. I want you to say this to yourself. I want you to know to do it. I don't want to just do it because I can do it. But if you're watching this video now and you clicked on this and you click this timestamp, you need to immediately go and look at the what for this assignment. You need to immediately go, ooh, it's here. You need to immediately go and look at the what as you're doing it. As you're doing it. This is your biggest help. When our graders grade things, they're literally clicking these buttons. Like when they're in the grading platform, they're literally clicking these buttons. So where do you need to go as you are making your assignment? The rubric. Taylor, 100 points right there. Go to the rubric immediately and look at where you're getting your points or losing your points. So if we look at what the rubric says, we'll read over the assignment here in a moment. The first thing you need to do in the executive summary is the reason why. Think about this. If you're going to give someone a report, you need to tell the company the goal, the research, like maybe to say who the company is, what you're doing, why you're doing this. That could be 1 or 2 sentences right there. Make them strong sentences. Don't just say like, we're researching candy because we want to, and we're the candy company. I don't know. We'll get the context here of this, but you need to be clear. You need to be like, we are Eastman Chemical, and we are doing research on blah, 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 to look at the tensile strength, the blah, 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 blah. And you want to be very specific and very clear and let them know why. The reason why the research being performed is not clear or nothing. So you could hit this if you're not specific. You don't need to go into like 10 sentences on it. But if you think maybe I wasn't specific enough, writing another sentence is never bad. This is the part of the explanation should orient the reader to who the company is, what they are researching, and why they are researching it. So right here, you need to tell them who the company is, what we're researching, and why we're researching. You could literally make each one of these one sentence. No graders should take you off for writing too much. Of course, if you write 10 pages on this, maybe they should. So I retract that statement. The next thing we need to do here is key findings. Now, the number one mistake people make when doing key findings is they don't give numeric backing. So with this right here, you need to give numeric backing. Does it not say numeric backing in here anymore? Did we change the key? You need to you don't want to just give the finding and say, we found this, oh, there it is, numeric backing. I was looking for that numeric backing right there. A lot of people do not give numeric backing, and this should probably say too many or too few, because not often do people give too many. You do want to summarize it. And maybe I'll tell Terry we should update the key to this should be like 0.75. I'm really not. Yeah, it is. Let me tell you why. You're doing an executive summary, so you're taking a report and condensing it down. Think about this. Would you rather read, Taylor, a 10-page report or a 1-page summary of that report? You're the head of the business now, Taylor. Would you rather read a 10-page report or a 1-page summary of the whole report with all the key stuff? Like, it starts out with like, hey, here's the company and here's what we're doing. You're like, all right, cool. Here's what we found. Okay, cool. The 1-page summary, right? So this is meant to take a big report and summarize it into something someone's more likely to read and understand what's important from it. So you don't want to summarize everything, because then you're just rewriting the report. If you take every finding and just put it in there, well, then they could just read the report. If you read the report and understand the report and can condense it down, then you're doing them a favor and you're basically creating like a Cliff Notes. Shout out to Cliff Notes. So, finding the right things, and make sure to give the numbers, what's numeric backing. Like, we found that people were 2 times more likely to buy this product. It went up from 38% of people buying the product to 76%. Quoting the numbers right there, saying, don't just say people were more likely to buy. We would say, oh, before advertising, there was 38% of people buying the product. And after we did the advertising campaign, 76% of our customers are buying the product. This was a 2 times increase. That's numeric backing right there. So you have to give the numbers, and quoting the numbers right there in your findings, telling people what's important, like this advertising campaign. I'm making up a fake story right here. This advertising campaign was a success because, and then listing the reasons. Right here, we have the action item. So I think if an advertising campaign was a success, we might be asking for what? I'm making up a fake thing right here. The action item is what you think the company should do based on these findings. The action item is listed in the executive summary and has some logical reasoning. The executive summary gives a suggested course of action. It needs to be based on the findings. So if a marketing campaign was successful, there's many things we could do. I don't want to say anything because then people oftentimes just write down exactly what I say, but you don't want to be vague. I'm too worried, like I might say something and then everyone writes down exactly what I say. But you're saying we should do this. You can be direct. You're talking to the company now. You're a big part of the company. You're an important part of us, of the company. And so you should tell us, here's my ideas. Here's what I think we should do. here's the backing. The backing will be in the numeric findings. And then because of the numeric findings, we are justified in our reasoning right here. And so with this, if you look at it, we've got a clear and concise right here. We've moved a little points over here. Clear and concise, approximately 5 to 8 sentences. I'd go more towards 8. If 5 longer sentences work, I'd go more towards 8. And it's not bad if you do 9. But yeah, it's very important that I would say 3 sentences here, 3 sentences here, 2 sentences here. Probably that's about right. 3, 3, 2. This could technically be 1, but yeah, that's probably about right. I would go towards 8. It's just, I mean, like a big compound sentence. This could be a big compound sentence. This could be like 3 big compound sentences, and then you could do 2 big. I don't know. Careful about going with 5 sentences. That's like the bare minimum, and 8 is like approximately between 5 to 8, meaning some people might could do 9. It's not bad if you do more. Just be very careful. Like, don't think I have 5 sentences, I'm good. You could easily write 5 sentences that just don't really give us key findings. You could be like, we found 5, we found 4, we found 2, and found 5 what? Found 4 what? All right. So that is the executive summary. We'll look at it a little bit here. I don't want to go into too specific lest I do the report. This is also where people make mistakes too. Now look at this. 5 through 8 sentences here also. When I look at a lot of the future research, oftentimes is 3, 4 sentences or a few short sentences. So you want to also give good reasoning. Now, the future research, and this is what people don't realize, is new ideas. I want you to say that with me. What kind of ideas are we talking about, Taylor, here? This is the future research. This is not action items from what we learned, because we just did a research project right here. We found out some stuff, and then we're going to do actions from what we learned. So we're like, okay, this marketing campaign was a success. So now we're going to, because of the success of the marketing campaign, do blah, 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 blah. But the future research is brand new ideas that go beyond, and this is the important part, go beyond the report. So when you think about future research, this is like you selling them things, ideas, and avenues. Companies want innovation. They want people to think up things outside the box. I mean, most companies, I assume. I mean, companies that don't do that are going to have a problem in today's world. So you're bringing to them your ideas about, hey, we could do this, we could do that, but shouldn't be directly connected to the report. I mean, you shouldn't say like, hey, we're Eastman, let's go make cars, unless you have good reasoning. If you have good reasoning, you could back it with that, but you should be thinking of things that relate to the company, that go beyond the report, that aren't just directly like, okay, we analyzed a marketing campaign. Oh, but in the marketing campaign, we found this. Do not go back through the results of the report. Do not go back through the results. Don't use the future research as like in conclusion, we found this, we found this, we found this. I've seen multiple people do that for the future research to be like, in conclusion, we found this, this, and this in the report. So no. This is literally like, where do we go next? And it's not here's what we found, what do we do next? Because that's what's in the executive summary. Future research is like, okay, beyond everything we've just talked about, what is our action? Like, what is our plan as a company? And you're giving your say for the company. So future research is, I like to compare it to like a Marvel movie when they have like the teasers at the end. It's something that is almost standalone. If you ever look at the teasers for Marvel movies, they add in this little thing at the end, and it's just like a little extra thing. So it could almost be disconnected from the movie, but it is related in some way. Like maybe there's one where Nick Fury appears at a bar or something, but he wasn't in the movie at all. So it's like, wait a minute, this guy wasn't even in the movie at all. He had nothing to do with the movie, and now he's here. So I think, Nick Fury appears at the end of Iron Man 1. He like walks in, he's like, we need to talk about the Avengers Initiative. So you can almost watch that just by itself and still be like, that's cool. So the future research can stand by itself. You don't need the report to understand the future research. And I think that's the best way. If you're still wondering, I hope people have clarity now on what the future research is. If you've seen Iron Man 1, you get to watch a really great movie. You know who Tony Stark is. You learn some cool things. There's a conclusion at the end, kind of like we know who the company is, what we're doing. We talk about important details. We give an action item. And then at the end, there's the whole standalone thing that has nothing completely to do with the movie because they didn't talk about the Avengers Initiative in the movie. It's still Tony Stark, though, so it's still the same company. And then Nick Fury walks in. So it's this brand new idea. It's this brand new pathway going forward that isn't directly connected to the movie, like not directly. So please, please, please email if you have questions. Let's go look at the report right here. It's kind of listed here, but the rubric is really where like our grader is going to click those buttons. So you want to go and click those buttons. Where is the files for this? Where's the files? Do we know if the files posted? After spring break. Terry, where's our files? Well, let me go see if it's synced. I'll go sync it myself. What is... Oh, Terry was emailing about this. He might have it up today. So if you're watching this, it might be literally up as we're speaking. I'm going to go to the blueprint that we have, the statue on blueprint. And I'm going to go look. Maybe I shouldn't sync it. He's doing 1 week. The blueprint. You're welcome, Jackson. So I'm over here in the blueprint course. The blueprint is where we send out everything from. I think it should be up later today, probably. I'll probably ask Terry. And thank you, Taylor, for asking. And thank you for anyone watching this right now or in the future. But you probably see your files. It's kind of good that I didn't have the files because we're just thinking of the general sense right now, like how to write these things. So an executive summary is literally somebody condensing a report down for you so that you can kind of read like a half-page or 1-page summary of a 10-page report and be like, okay, that's the important stuff. That's what we're going to do. Good, 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 good. And then at the end of it being like, well, here's some new ideas, which is the future research down here. So very, very important to understand what these things are and how to do them. Does that make more sense, Taylor? Your thoughts on any of this? Do look at the rubric. When you're thinking, am I going to get my points for the executive summary reason why? If you're just like, we're this company and we're doing this, yep. So make sure, look at the rubric and be like, which button would people click right here? And then the numeric backing is where people really lose points. And I wonder if Terry would be okay if I like updated the rubric. Let me email him on that right now. Let me say, what if we did too many is like 0.6 or 0.7 and too few is 0.3 or 0.25? Because a lot of times we'll give too few findings. Let me email Terry. Emailing Terry as we speak. We go. Yeah, he was posting today. He literally said that in the email. Looks great. For the rubric, what if we give 0.75 too many details, 0.25 too few details, no numeric backing. A lot of times students give no numeric backing when giving key details. Okay. There we go. Emailing Terry, sending email. That's good stuff right there. Well, what other questions do we have? Woo! Might do shorter office hours today. Never know. Got confidence rolls coming up right here. I'll speed one on the homework. I don't know. Maybe that's bad for people when I speed run it, because maybe then there's like, I don't need to know the concepts. Maybe I'll teach a little bit about confidence rolls right now. Because a lot of the problems are very similar. That's the thing to notice. Is like when you learn how to solve a problem, maybe I'll do like one problem really in depth. And maybe that's better than speedrunning. I don't know. I'm trying to figure out this whole teaching thing. I want people to understand the material. It's not just about solving the problem. I keep saying that. It's not about solving the problem. It's knowing how to solve the problem. You go, well, if I know how to solve the problem, what's the point? then you can solve any problem like it. Then we don't have to worry about solving that one problem. We know how to solve problems. So let's see right here. We'll look at a homework question right here, and I'll pick one of my favorite ones, probably, that kind of shows all the topics. Okay, so I'm trying to find a homework problem right here. So knowing how to solve, let's call this segment, knowing how to solve Stat Tool 1, chapter or homework, confidence intervals or proportions. Okay, so I've been reading over the advice that the students who made an A on the test gave, and I want to do a slower work through of a problem right here, and I want you to understand like why we're doing this. So all these problems here are going to have a very similar structure and give you a lot of similar information, and so we need to know what we're given and what we're trying to solve for and why we're doing it. So let's take a look up here. It says they took a poll of people. A poll conducted by the UC Berkeley Institute of Governmental Studies in 2019 found that 52.3% of the 4,527 respondents said they considered moving out of state. Complete all these parts. Now, before you start completing the parts, you have to understand what they did. So here's what they did. They went up to people or emailed or did something and said, got a little person with a clipboard right here, and that person right there said, are you considering moving out of state? So that's what that person said right there. They said that. And this person said, no. Or maybe yes. So this is what we have to realize is going on right here. They went up and said to people, are you considering moving out of state? And then 52.3% of people said yes. So that person said no. So then what does all this information up here mean? Well, first off, knowing this right here is going to tell us that the variable we're working with is categorical in nature. It's categorical because we're going to have the responses of no and yes. So this is going to be a huge help for the problem when we get to the notation that we're going to be using right here, because if it was means, we'd be dealing with like mu and y bar. But in this instance, we're dealing with other notation, which gets us to what we do next is we start marking the notation. 2019 doesn't matter. It's a number.
It doesn't matter.
It's just the year. And with this right here, we have 52.3% of the 4,527. So this is going to lead to this being the sample size. So lowercase n is the sample size, and this is the sample proportion. Now, it's not the truth because we're asking people, I believe in California, because it's UC, so University of California, Berkeley, what percent of these people in California are planning to move out of state. There's more than 4,527 people in California. That's just a sample from a poll, and the poll lets us know this is a sample. Now, what we want to know is from a sample, if we only have a sample, we use that to make inferences about a population. And we call this inferential statistics. So you have over here p hat, which is the sample proportion, is going to allow you to make inferences about the true proportion, if you remember from earlier semesters. Now, the problem is we don't know the true proportion because that's what proportion of all people in California want to move out of state. We have no idea on that. But there could be problems. So this was conducted, and let's think about what problems could be in this problem. One, it needs to be a random sample. What if they talk to college students? So think about this. It kind of would make sense that if they talk to college students, a lot of people plan on moving out of state because, you know, they go to college and then they move or something like that. So the question would probably need to say random. You would think the polling organization. So it might say, you know, what did you assume? We would have to take random individuals. So probably they did that, but it would probably need to state that. Also, sometimes on my Pearson, they assume independence. So you'll see that in questions. Sometimes they'll put random and independent side by side because if it's independent, it'll be random. And if it's random, we have to assume they're independent of each other. I just use random as a catch-all for we randomly took individuals. The 10% condition right here says that we take less than 10% of the population. Now, what this means is that n, lowercase n, is less than 10% of capital N. So we know what lowercase n is. Lowercase n is up there in our notation of 4,527. So the question is, did we take less than 10% of the population of California? Because that's capital N. We're trying to understand people in the state. So I would say there's good reason to believe that there's more than 45,270. You can also take this and times n by 10 to get in to see if there's at least 45,270 people in California. You're all right. So that's another way to think about it. Also, states have, California's probably got like 50 million, something up there. Easily a couple million. So we've got taken way less than 10% is the point of that. The third condition here is where we have to pause. The reason we pause is because the third condition is always going to be related to what kind of data we're working with. So when we pause right here and we ask, what's the third condition? We have to think, okay, I'm working with categorical data. So categorical data is what we're working with. It's not going to let me do it the same way anymore, is it? No. Here we go, right here. We'll go 3, 4. Yeah, okay. It's going to have to look weird. Okay, third condition. I really like things to look pretty. It's a problem. And nope. Okay. Third condition is a little sub-indent. And with this right here, try again. I don't know why I care this much. Sorry. You're watching this in the future and you're like, come on. Okay. Let's just make it. I'll spend an hour on this probably. There we go. Much better. Okay. Third condition. Good. Is success, failure right here. And that means we need at least 10 successes, at least 10 failures. And the problem is we first learned this condition as NP is greater than or equal to 10, and NQ is greater than or equal to 10. But here's the thing, we don't know P, and if we don't know P, we don't know Q. We don't know the truth. We're trying to infer the truth from a sample. So we have no idea what the truth is. So instead of using NP and Q, maybe someone's thinking this, because we don't know the truth, we have no idea what the truth is anymore. So since we don't know what the truth is, instead of NP and Q, we're going to use, wait for it, NP hat and Q hat. The earlier chapter used NP and Q because we knew them. In this chapter, we use NP hat and NQ hat because we only know the information from the sample. So at this point, we don't know P. I mean, we might, if we could take all the data, we'd need a census. So we don't know P, we don't know Q. We do know the sample proportion up there. One last bit of notation I do want to point out, it might not be needed for this problem, but let's point it out, is we can also find X, which is the amount of people who said that they were going to move out of the state. That's because X over N equals P hat. So what's interesting is this right here is actually the formula for X. Look at the algebra right here. If you do this, that is the amount of conforming or amount of successes in the sample. So when we solve this quantity out, we are actually solving for X, which is the amount of people in the sample who said they're going to move out of state. So 0.523, and you can see the formula up there, times 4527. And just they didn't maybe carry enough decimals, but 2,368. 2368. We do like to talk about our tricks right here and ways to know stuff. I can actually find the other value. Good to see you here, Jesse. We're doing a big in-depth example, and I'll be doing another one. There's Q hat right there, and I'll show our NQ hat. And 2159. There it is. So we have at least 10 success. This is test 3 material, Jesse. So you're like, wait a minute, success failure condition? Wait a minute, we were just doing that. So we have at least 10 successes, at least 10 failures right there. And that's the values. And once again, we can just times Q hat. Well, let's get Q hat right here. We should have found that at the start. Q hat is 1 minus P hat. So 0.523 and then 1 minus, really, there we go, 0.0477. We can double check our math down here with our trick that we used to find it, and we can times that by 4527, and there it is right there. And the reason I know this, or I did the trick, is that NP hat and NQ hat will add up to N. So if you add those two numbers together, you will get the full sample size, because you're just taking a percent of it that adds up to 100, because Q hat and P hat up to 100. So when you times it by N, you're just finding out how many successes, how many failures were in the sample this time, because it's P hat and Q hat. So now we get down to doing the formulas. So the formula for this is going to be P hat plus or minus Z star, and then we have square root P hat Q hat over N. And with this right here, it's important to know the three parts of it. This is the estimate. This next thing is the confidence level. And the last thing here is the standard error. Basically standard deviation. So there's three parts to this. Think about why we call P hat the estimate. The estimate comes from a sample and would be your best guess of the truth. So if someone said, well, what percent of people do you think are probably going to move out of state? You say probably about 52.3%. You say, why do you think that? Well, that's what our sample said. That is my estimate. The sample proportion estimates the truth. But the remaining portion of this gives you what is called a margin of error, because every estimate has a certain amount of uncertainty in it. And the margin of error is governed especially by two things: your level of confidence and your sample size down here. So as your confidence increases, it will decrease. And as your sample size, margin of error will, excuse me, I want to not say that wrong. As your confidence level increases, I don't know if I can graph that here so perfectly. As this increases, your margin of error will your margin of error will increase. There we go. Wow, reversing things. As your sample size increases, your margin of error decreases. So let me repeat that so you can hear it. As your confidence level increases, your margin of error will increase. So as this increases, this increases. And just look at it mathematically. If Z gets bigger, plus or minus Z times something. So as Z gets bigger, this whole thing gets bigger. Since this is in the denominator, as this gets bigger, the margin of error, that's why I'm connecting it over here. As N gets bigger, the margin of error decreases. This is the two things that control the margin of error. P hat and Q hat control it, but we don't really control that. We can't really change what the sample says. We can change how many people we talk to. We can also change our level of confidence right here. So those are the big things we can actually have impact over, changing our level of confidence. Which brings us to the concept of, well, what the heck is this level of confidence? And you'll notice it's related to a z-score. So when we talk about how confident we are, it's basically how many standard errors we're going out on the curve, which is also related to the z-scores right here for standard deviations. And so when you look at this, we can go to the between, because we're making a confidence interval going plus or minus this amount. And if it asks us something like 90, we can get the z-score. Now, I highly suggest putting a few decimals on here, like 4 decimals. So this would be 90% confident, 80% confident, 95, 1.96 classic, 98, 99. And notice as you get more confident, the interval gets wider because you're covering more of the curve. Like the value you're looking for is more likely to be contained, and that's a key phrase right there, contained in this confidence interval. So the higher the z-score, the bigger the curve, and that's why the margin of error is getting larger. There's a lot of classic ones we use just to show again. 80%, 1.8, 1.2816, 90%, 1.6445, and then there it is. It was 449. Ooh, I got it wrong. 95, 1.96, 2.36. Wow, 32. Wow, I'm just gonna stop saying numbers. You can see it gets wider right there. And there's the ones we usually know, like 68 is basically a z-score of 1. Basically, we'll change the decimals here. I'd use 4 decimals if I were you. It's basically 1. 95 is basically 2, and 3 is basically 99.7. The next one is, or if you do 3, it's going to be, so it'd be 99.73. There it is right there. But 68, 95, 99.7, the more confident you are, the larger the z-score. So this literally relates to how much of the curve are we graphing, how much of the area is contained in the middle of the curve. So now that we have all this written out, we just need one last thing, and this will be basically a one-page sheet of how to do these problems if we get to write on it. Darn it. Here, let's go and no. Okay, good. Okay. And so now, we'll delete those here in a moment. I am blank % confident that the true blank, who is the big blank we got to do, is contained in the interval blank to blank. This is the interpretation we need. And this is where people will be writing things out on the final. So if you had issues with interpreting things on this test, this is the interpretation, one of the interpretations we do on the final, and it's interpret confidence intervals. I am blank % confident that the true blank is contained in the interval blank to blank. We'll be interpreting this here in a moment. My Pearson will have you usually click through the choices, but we've kind of just created a one-pager for this problem right here where it shows how to do these it shows how to do a problem like this and covers pretty much all the concepts. This is the confidence interval for the true proportion and understanding what we are doing, and now we can solve this problem. So let's take a look what the problem asks. It asks right here, compute a 90% confidence interval. So we know our notation. We need the z-score for 90% because that's going to be important for us to get the computation. 1.6, and I would do 4 decimals, 449. So there's the z-score. We're going to go back here to our notes and go to our z-score. Plug that value in. The star means you get to pick it. If you're wondering what the star means, it's based on the level of confidence, which the researcher can be like, I wanted this % confidence interval. These values we've listed up above in the problem. So this one was 0.5. Here will be the black pen. 527. Hey, what's up, Carlton? Maybe that was a... See, I got the wrong numbers. There we go. What's up? Delete that for the moment. Sample size. There we go. So now we just solve the interval. It's going to give 2 numbers right here. We'll put it into the interpretation 2. So we're going to go 0.523 times 0.477 divided by 4527 and then square root times by 1.6449. That is the margin of error. So we could 0.0122. That's the margin of error. And there's this. And so now let's go 0.523 plus. And there it is, 5352. And then do the minus. Oh, did I carry enough decimals? Oh, wait, 0. I think I've got it saved. There we go. 5179. Let me double check. 0.8. Should be enough decimals. She'll look how many decimals I wanted. 0.80. Worst 0 ever. A lot of people on the test have a hard time with this part. The middle part right there is we were asking people, do you think you're going to move out of state? So I'm 90% confident the true proportion of people who plan to move out of state is contained in the interval 51.08% to 53.52%. I am, and I do this as a percent usually, we'll see if it wants decimal percent when we enter it in. I am 90% confident that the true proportion of people who plan to move out of the state of California is contained in the interval 0.5108 to 0.5352. And that should be everything we need for the question. So they are doing it as this. I think it was 5108. It says to 1 decimal. So that does round to this for that one. Let me check. There it is right there. Hopefully we did all the algebra right. and then 53.5. 53.5. Did we do the algebra correct? The answer is yay, we did the algebra correct. And now we get to their interpretations. I like to say I am blank percent confident. And they'll say one is 90% confident that the true proportion of Californians who consider moving out of state. And I want you to just understand like the similarities between what we wrote and what they wrote. You don't want to just click on their answers. You want to write your own sentence right here. I am 90% confident that the true proportion of people who plan to move out of California is contained in the interval blank to blank. And they're doing the same thing right here with their answer. They're just filling it out for you. So you want to write this out, you want to practice it. These are written interpretations that will be on the test, so you won't be shocked by them when they appear. There's the rounding of it right there. 53.5, that should be good. Yep, I am blank percent confident. Since high cost of living and housing has been cited as a reason for why people move to states, but the state government will consider investing in a new, if it's reasonable to believe that more than 50% of people are moving out of state. Well, we think the truth is in here. This is interesting because this leads into rejecting values or not rejecting values. We would think that more than 50% of people plan to move out of state because our interval suggests that, because the interval is entirely above 50%, and that's what they're going to say. Since the confidence interval is greater than, completely above 50%, the state government should consider this because they're going to do it if there's good reason to believe that. So they're then asking you to kind of test a value on that question. So really, a lot of these questions relate to understanding the information presented to you and what it has. So if you look at this question right here, it's very similar. Well, actually, it's too similar, I think. It's literally the same context. This one right here gives the donations. And if you look right here, we have basically 95% confidence interval for this data. So what I can do, since I know the formulas, is I can find, first off, what p hat is, because that value is x. There's p hat. There's q hat. So p hat times q hat over n, square root, that's the standard error. 1.96 is the z-score. There's that. That's the margin of error. So 0.048781 plus the margin of error is that. So 4.91. And there's the upper of the interval, the upper portion, and 0.0481 minus, there's the lower, 4.65, right? Oh my gosh. And that should do it on that. Given the confidence interval, do we think that's plausible? No, that's outside the interval because it's not contained in the interval. And is that it? That's that problem. So this is the point right here. If you know the formulas, you know what you're looking for, that this is x, that is n, and then we can find p hat from it to estimate the... Whoa. Audio going, music in the background. So if you notice right here, we can easily calculate these things using the information provided to us. And that's kind of what's key, is we have right here n, we have here x, and when we can find it, we can solve these problems. Knowing what you're looking for is the key for these problems. This is the lower, this is the upper, and then they're asking about confidence levels and what it means right there. So some of them have a different format. The true-false is a good fun one. But then, you know, if you look at something right here, let's look at a multiple choice. If the level of confidence increases, the confidence interval will what? It'll get wider. It gets wider. That's what happens. That's the z-score. So that was the z-score concept we talked about right here, where if we increase the level of confidence, the confidence interval will get wider. Just more confident, wider interval. Is there another multiple choice? I love multiple choice. Which is the same correctly interprets what it means to be 95% confident. So confidence intervals are not about one interval. They're about the repeated process of making intervals. It's not that we think one interval contains the truth. I said over time. Well, 95% of the time, no. It's not that it'll be in the interval. 95% of samples will produce confidence intervals. This is about the creation of multiple confidence intervals over time that capture the true proportion. So it's not about one interval. 95% of the samples contain the confidence interval. No. It's about the repeated process of making intervals. And actually, Enes showed a really good thing on this. Let me grab Enes's app. He showed a really good animation. So here's confidence interval demo. Perfect. I need to show this in class today too, probably. And so here we go. This is going to, we'll just use the normal right here. And let's start sampling. So the truth is this value right here, and that's mu. And if you notice, the green ones contain the truth and the red ones do not contain it. So we are creating right here, we don't want to do bootstrap intervals. We're creating 90% confidence intervals. I think they should make it nicer on the notation. But samples taken, random samples taken, 90% of intervals created from random samples are expected to contain the truth, or will. I hate using will in statistics. Statistics says that 90% of the time, random samples will create intervals that contain the truth. Like these red ones right here do not contain the truth. Mu is the true means. This is actually quantitative data right here. We can do it with proportions too. If you look over here, we can hover over it. Ooh, when we stop, it should be close to 90%. Yeah, it's pretty cool. And does that make more sense, Jesse? I might use it today in class. If you notice, the more spread there is to the data, the greater the range is, because that's more standard deviation. So we'll watch for one. That was really close. You saw that one right there, that red one? That was super close. Like I'm watching the dots spread, and that was super far. When's another super close one? Let's find it. We want one with a very small standard error. That one was pretty small. I'm waiting for it. Yeah. I'm waiting. There was one that appeared right in that moment. I was like, look, super small standard error. That one, it's pretty small. Let's look for a large one, large variation in the data. That right there, I saw it right in that moment. That one's a large one because you have more uncertainty when there's more spread to the data. So we'll go ahead and stop this right here. And 84%, I feel like something's a little bit off on their simulation because I could do the same simulation. I can't make it all purdy like that. But I could do the same simulation, like literally take from a data set. If I were to do it, I could probably animate it after a while, but we'd go right here and we would take random normal data. We'd take 1,000 data points and we'd say the mean is equal to 85 and the standard deviation is equal to, let's say, 10. Cool. And with this data, it looks like the following, and the mean of the data is basically 85. There is some variation, so let's go a little bit higher. That way we get less variation with more samples. It's basically 85 for all intents and purposes with 100,000 observations in the population. So we'll just think of the mean as 85. So what we're going to do is we're going to go here and sample from the data. We'll sample 50 observations. And so from data, we'll sample from data 50 observations. And there's random 50 observations. Now what we can do, and what's really cool, is we can do t.test on this. And the t-test is how we make a t-interval. And there is literally the interval right there. And notice, what is in that interval? So Jesse, I hope you're still watching. What is in this 95% confidence interval? Let's pretend this is like test score. I am 95% confident the true test score for students is contained in the interval 80.56 to 86.31. So what do you notice is in that interval, which we lucked out on this? If you notice what's in this interval, the true mean. That's the true mean because we created data that has a true mean. That's the true mean of the data, basically 85 right there. We're just going to call that 85. And it's actually contained in our interval to estimate it from a sample of only 50 points. We just took 50 observations and we were able to get an understanding of what the true mean is and narrow it down to some value. We think it's somewhere between. This is a different sample now. Ooh, it doesn't contain the truth. Dun, dun, dun. Because 95% of 95% confidence intervals will contain the truth. So if we repeat this process, you notice that one does, and this one does, this one does, this one does, 95%. Ooh, that one doesn't. We've seen like we're getting a lot that doesn't. But if we want to see if it's true, we can do something fun here and do a for loop. So let me go here and store this as output. And this is something we might do in upper level class or have the understanding of how to do. I think, whoops. This is a list, right? And confidence interval. And now we want to go to the lower. And we want to go to is 85 contained between. So 85 is greater than the lower, and 85 is less than the upper. And that'll tell us if it's between it. That's true. Okay. So this is check. And we'll put it in parentheses. So now this is the check. Like I said, I can do this, but I can't make it pretty with animations. I'm not that good yet. And so that's got that. We need to go to check position 1 because we're going to do this multiple times. I know that says I, but I will go through the vector of 1 through 1,000. And we're going to do this check 1,000 times right here. So with 1,000 runs of this, creating 1,000 intervals, doing this check I did right here 1,000 times, we can see right here the percent of time it got it was 94.2. And of course, that is just one instance of doing 1,000 checks. Now it had it 94.7. If you notice, and what's really funny here is we can literally run the check multiple times by doing this 4, and we're going to do J here. We'll run the check 100 times, which is more than enough because this does take a moment to run. And then we store out here, the mean of the check is going to go into double check. And that is going to go into position J, but we haven't made that yet. And that'll be not MO, that'll be mean of check. And double check needs to be created. Double check, and double check will be a blank vector. And now we should be good. And this is now running the simulation I did of it's simulating a simulation 100 times. So we were simulating confidence intervals 1,000 times, and then running the simulation of simulating 1,000 confidence intervals 100 times. So a lot of calculations being done. It seems like it was only taking about half a second, so I've only got probably another 30 seconds here to talk. I could have done a system time on it to see how long it's taken. But the double check is going to create a histogram centered around 95% because there it is, and there it is, literally centered around 95%. And we can see what it looks like that pretty much 95% of the time, 95% of the confidence intervals contain the truth. And it's not about one interval containing the truth. And it's just so cool to see this in practice. Like if we did a larger simulation, for 500 points, does anyone know what law we were just dealing with? So if I increase the amount of simulations, which was on last night's test, we're actually dealing with a law, which is so cool that simulations actually show this. We can actually show via simulations that 95% confidence intervals will contain the truth 95% of the time in the long run. It's not about one interval containing the truth. It's about the long run repeated process of making intervals. I might say the law here in a moment. But basically, by me doing more simulations, extending out the simulations, doing simulations of simulations, I am basically dealing with how does the mean for last night's test look so far? So the interpretation is probably mid-70s. Probably pretty good, Jesse. And I think I've graded a few interpretations of people's. We'll see if there is a curve or anything like that, but I'm pretty happy with it. I should look at the past means, but I'm hoping we're one of the higher classes. Sorry, other classes. And this would be the law of large numbers, Jesse. I'll throw you some 100 points right there. But we just dealt with the law of large numbers right here by me doing simulations. Because watch this. If I bring this down here to 10 and bring this to like 2, then watch this. If I rerun all this right here, I have to recreate the data because let me store here check as its own blank vector because we want it to be blank. That way it redoes it. So now when I do this, what? Exactly 95? No, wait, what? I got lucky there. See how it's 90%? So with very low, 80%, or if you go really bad with like very small numbers, like we'll bring this really down to 2 and 2. Now the simulation is going to look like 100% of 95% confidence intervals contain the truth, 75% of 95% confidence intervals contain the truth. It'd be very hard to get 0%, but it could occur. 75% of 95% confidence intervals contain the truth. We would need a 1 in 400. Is that really? We're looking out on this a little bit. But yeah, you could get that 0% of 95% confidence intervals contain the truth. Oh, let's go really low numbers. Here you go. Now when we do this right here, we might see 0% of 95% confidence intervals contain the truth. Which this is the kind of reverse side of law of large numbers, that we're not getting a good estimate of the true probability of something. Oh, there it was. Darn it. You have to do it around 20-ish times, or 1 in 20 times. Now it won't do it for me anymore. It's not more likely to do it each time because these are independent trials right here. Each time I do this, it's not any more likely than the... There we go. I'm just going to talk to it and be like, it's not more likely the next time. That was gambler's fallacy. Yeah, what's the most missed question? It's a good question here, Jesse. Let's go talk about that a little bit here. And most missed questions. I wonder, it should give me... The way it does reports is never really amazing. Like, I don't think it shows me like what questions were missed, but it's funny. Kahoot does like a little bit better of a report showing like most missed. Okay, let's take a look. And here we'll change the concept of the video because now we're not talking about confidence intervals. Did I just close out? No, I didn't. I got too many windows open. Let's see. What time is it on the thing? It is 1:12:33. Talking about the test. There was a very commonly missed question. I know one off the top of my head that a lot of, and there's actually one good analysis that it gives, just one good analysis. There's this really good analysis where you can see if students who generally did well on the test got a question wrong. Does that make sense, Jesse? Like you can see students who generally did well on the test, did they get this question wrong? That's a really good analysis. So it's like, okay, here's the question that like why are people getting it wrong? And it deals with the following. And I alluded to it in one of the reviews because I know it's a tougher question, but it's a tougher one. And maybe you'll be like, oh, I remember that. Okay. So tell me how to finish the sentence. As the sample size increases, the blank will become more normal and tighter. As the sample size increases, the blank will become more normal and tighter. As the blank increases, as the sample size increases, the what will become more normal and tighter. The shape of the what? The shape of the what? We could say that. The shape of the what? The shape. Well, yeah. Mm-hmm. Of the what? This is the specific part where usually the error is made. The shape of the what will become more normal and tighter. I'll give you some hints. Well, the histogram, this is the hint right here. I mean, I'm alluding to it. Okay. So there's very small differences between these sentences, right? Parent population, sample data, and sampling distribution. So which of these becomes more normal and tighter? This one. And let's talk about why. Okay. So sampling distribution, exactly. So here's our notes over here. And then here is our very famous applet right here. So if we look at something that is very skewed and we take 25 observations, the 25 random observations are probably going to look what? So the parent data is very, very skewed. The 25 random sample points will probably look what? The 25 random sample points will probably look what? There's 25 random sample points. The 25 random sample points will probably look very what? Well, they'll be random, and they'll also look what? Spread out. So they'll look like whatever the parent data looks like. The parent data is the original like population. Sometimes called the parent, what it comes from. It goes like child data or whatever. But this is the original data, and we're taking samples from it, and it still looks skewed right here. But the sampling distribution is what can happen theoretically over repeated sampling. So you can see right here how I have it listed, and I'm trying to connect it to where the colors are at for this. We'll put, yep, that's up there. So these are not true. As the sample size increases, the shape of the parent population will become more normal. No, the sample we take has nothing. It will not change what the data looks like. Does that make sense for the top one? The parent data or the population data, or you could just remove parent right here if you wanted and just say population. The shape of the population will become normal and tighter. No, the sample is not going to change what the data looks like for all the data. As the sample size increases, the shape of the sample data will become more normal and tighter. No, the sample data will look like the population data up here. As the sample size increases, the shape of the sampling distribution will become more normal and tighter, and that's down here. Does that make sense, Jesse? That's a pretty tough question because there's just that small change to the wording. And I think people remember that it becomes more normal and tighter, but what becomes more normal and tighter It's the sampling distribution right down here on the bottom. Yeah, and that's a super tough question. A bunch of people make A's and miss this question. So that's I alluded to it in one of the reviews, and I think I did a teaching the test moment. So yeah, it's 63. Yeah, it's when the there's grading done on the whatchamacallit. But what's really interesting about the grades is, what do you notice kind of in here, Jesse? And this is something that, and I'm trying to find out. Someone has a 63. Now, these don't have the interpretations graded, which are up to 12 points. And well, I think I looked at a few. So some people have had it graded. But there's very few people with interpretations graded right now. So there's very few. So I look over a few tests, make sure things are going all right. I really see like a peak here and a peak here. And you know why? Why is there some bimodality to this? Or you can even say maybe there's a peak over here. I don't know. It's hard. You don't want to say there's too many peaks, but I really think we have at least one peak and two peaks. I'm happy this is the higher peak. So that's one of the classes right there. I guess I'll grab the other class, bring it over. They have a 66 average, which are kind of close. We could do analysis to compare, but also you see a little bit of the bimodal shape here, and you also get that strong left skew. There's really this strong left skew to the data, and that person did get grades. So someone made 100. I think we might have a few hundreds, and I'm very happy with that. But you've got the two peaks here where you see a peak around the 80s, and this is pre-grading the interpretations, and then you see a peak in the 65s. So that might be around 8-ish points. So you're looking at a peak in the low 70s. And then this might be another 8 or 9 points. So 89, just going. So you got like your C's and you got your high B's right here. So really that's where the class is centered around. And then we do have the kind of left skew to the data. And the reason I'm adding on kind of the grades. How's this all looking, Jesse? Is it making sense? And I want to understand why people end up in these peaks. Why do we have this down here? Why? Yeah. And so this is the analysis we do when we get data, understanding what's going on with it. And I'll show you like one of the questions and how it looks on my side when we see the results of it. I'll go find one that people didn't do well on. So negative. Oh, is there no negative? Ooh, that's a really good sign if there's no negative. I swear there's negatives on this. Oh my gosh, did we eliminate all the questions that have a bad... Whoa. Okay. Apparently, we might have eliminated it. Eliminated questions that I don't think it's too bad if I show like 1 or 2 questions. Not the end of the world, right? Okay. So here's a question right here. It would be appropriate to predict a person's weight based on their height. It'd be appropriate to use linear regression. So what is this getting at? It's appropriate to use linear regression to predict, and I'll show over here on the side. It shows the 0.03, the positive. It should be higher up. The closer it is to 0, or if it's negative, that's bad. Discrimination analysis, like trying to figure out if people understood the question. But why would it be appropriate here, Jesse? And the key thing here is linear regression. Why is linear regression appropriate? And you could basically say the answer with two letters in the chat. Why is linear regression appropriate right here? And so why is linear regression appropriate? And so maybe a few people who did well in the test got this wrong. That could be the reasoning. So why is 2 quantitative variables? Boom. That's literally it right there. 2 quantitative variables. So 2 quantitative variables, it is appropriate. If we have 2 quantitative variables, we can do linear regression. Oh, well, it's interesting to see. Yep, there's the one I talked about. Talk about this one here. I'm going to take a screenshot of it and bring it over. So this is another one that had a lower miss. And I try to go over these a lot to make sure people know how to do these. That's my goal a lot of times. And so let's talk about what we practiced right here and tried to learn, like to make sure we can solve these problems. Suppose event A is it takes 15 or more minutes to get to work. And event B is it takes less than 15 minutes to get to work. So less than 15. So 15 or more. And then this one is less than 15. Okay. It says, are events A and B said to be, and then they're just giving you both words right here. Either word's fine, i.e. disjoint. And so what do you ask yourself when you do a disjoint question? If you're asking if 2 things are disjoint, how do you then examine this? So you would say, if one occurs, the other can't occur. So you would say, if it takes me more than 15 or more minutes, and that's exactly it. And if you look, this was a question, and if it was 50-50, that would mean it was a guess. So, I mean, 77 is not bad on it, but when you write it down, you're like, okay, it takes, and what do you notice about it? It's either going to take you 15 or more minutes to get to work tomorrow or less than 15 minutes to get to work tomorrow. And so what do you notice as long as we say you get to work? So what do you notice about these two things? Like, it'll either take you 15 or more minutes or less than 15 minutes. Are there any that were, I could look. I don't think there were any true falses. There might have been true false that was close to 50-50. I'll take a look here in a second. This is the one, though. The discrimination analysis lets us know, like, if students who generally did better on the test had a harder time with this problem. So this was one of the ones that, which is a bummer to me, because I hope we cover these very well to be like, yep, and they're also pretty much compliments. Does that make sense too? And compliments are disjoint because it either takes you 15 or more minutes to get to work or it doesn't, which means you took less than 15. As long as we say you got to work, it might even, we could add in like, given you got to work, given you go to work tomorrow, it either take you 15 or more minutes or less than 15 minutes. So they're oh, it's not bad to know that, but not all things that are disjoint are compliments. Like, it could take you 10 minutes, it could take you 12 minutes, and those are all disjoint. Like, you can't take 10 minutes to get to work and take 12 minutes. And we're saying, like, exactly, like, I got here in 12 minutes, I got here in 10 minutes. You'd be like, well, you can't do both. You do one or the other. Let me see. Can I search the percent? Oh, I can search percent. Okay, so. Okay, there was nothing exactly 50%. 52%. Ooh. Okay. I knew it. I knew it. I knew it. I knew it. Whenever people get to condition 3, what do they always put? Whenever people get to condition 3, what do they put? Whatever. This is just helping me too, Jesse. When people get to condition 3, what do you think they usually put? People get to condition 3 and they do what? What do people usually, they go condition 1, condition 2, condition 3, boom, success, failure. And look at where the wrong answers are right here. This is why I do what I do, because I know the problems people run into. What do you do before you get to condition 3? What do you do before you get to condition 3? Before you get to condition 3, you do what? We always do it. Pause. Sloan right there, 100 points. We know we pause, right? And so we pause, and I want you to think about this. Really, there's only 2 answers right here, right? If you answered the other things, that's okay. We've never talked about alpha, beta, delta. We didn't mention that here. None of those answers. So maybe someone's seeing some QQ straight enough outliers, plot doesn't thicken, but it's almost a 50-50. It's a 50-50 if you know the concepts to be like, okay, sampling distributions deals with these 3 conditions. So it's basically 50-50, but then 52% of people got it right. But we always say in class, we pause. Yeah. Probably by the end of the weekend, I hope. Thank you, Sloan. They have 1 week to grade them, and then I start to say, hey, we need those graded. That's when they get emails from me. But within a week, I bet. And then also I'll be sending out I probably need to send that out after things are graded. That way people don't, they don't have more questions. I mean, could, but yeah, I'll figure out how to send it out to make sure people can do it. I swear, I can't see these days. I should get that graded up soon. But this is where, and so Jesse, did you feel well prepared? We'll be talking about this at the start of class. We'll probably spend 10-ish minutes talking about it max. And I'll throw out some big points today in class I want people to show up. It's very important because we're not done yet. We got more classes. But something, how do you feel? Oh yeah, we were looking over that. They're pretty good. I mean, like, I think people who come to class generally get between 10 to 12 points on the last 3 questions. And if you think the graders are unfair, let me know. But generally speaking, on the last few questions, they're pretty good. But we really try to set up, if you're watching any of our videos, I look over the test all the time and I see where people make errors. And then I'm like, okay, that's where I came up with the pause thing a long time ago and put the pause in the chat. Because people usually just say success failure for the 3rd condition. But you'd be saying, why is this not success failure? It's that, because we're doing the sampling distribution for the sample mean. Oh, it says, yeah, well, yeah, sample mean for a sample mean. Are there any, well, I'll ask, are there any conditions for calculating Are there any conditions for calculating those? I think that was another commonly missed question. Are there, yep, it's the mean, exactly. Are there any conditions for calculating those? P hat and Y bar. And there's also a question like, what is P hat? That's just sample proportion. Are there any conditions for P hat and Y bar? No, it's just what percent of your sample and the sum of the observations over the sample size. Like if you had, the age of individuals like 18, 20, and 22, you would add those up, divide by the total, and then right here, if you talk to 5 people and 2 of them own bunnies, you could find the sample proportion of people who own bunnies. So this is 40% of people own bunnies, and this is the average student I talked to is 22 years old. So the sample proportion of bunny owners, 40% from the sample of 5. The 3 people I talked to had an average age of 22. And so knowing the notation, soon as I see mean, I'm like quantitative plus formula sheet kind of, yeah, exactly. Yeah, Sloan, that's really great stuff right there. And I hope knowing the formula sheet, knowing the formulas, understand what you're seeing and maybe seeing some context like 2 people out of 5 owned bunnies. That is 40% of my sample of 5. I talked to 3 people, so you can sum up their ages. I made it, oh, whoa. I don't know how to do math. That's the problem here. I think we found the problem, and it's me. There it is. I made it symmetric. That's a symmetric histogram of data right there from 18 to 22. So with this, that is, and I think understanding the formula sheet, understanding the notation is a huge help. It's like knowing the theory. On the exam, I had 2 questions of the same. Is that normal? Were they exactly the same? Let me go look at that, Jesse, real quick. So I'm going to blank the screen. I'm going to look at your test. Do you remember kind of what they were about? Someone might have put 2 test question banks that have the same. Then it's just kind of worth more points. Let me bring the test back over here. Let me go find your test. We'll chill music while we do this. Let's see. Pretty sure. Do you remember anything about the question? If you remember anything about the question, it'll help me find it. Anything? Similar questions? Yeah, a lot of them can be similar. If there's an exact same, then I want to probably change the test a little bit or like remove it from one of the banks. Sometimes when people add questions, they'll sometimes write the same question because we add and subtract questions as the test goes on. So it's not the exact same every year. But I've seen where someone puts a slope of 0. Slope of 0. Okay, cool. And what does a slope of 0 generally mean? Okay, here it is. Oh, do we put? So there's a 1 pointer right there. I see 1. Oh my gosh. You're right, Jesse. Given all relative conditions are relevant conditions satisfy a slope. Oh. I need to move that from one of the test banks. Why is that in there twice? Which we did cover this really well. So it was a 1 pointer, and that kind of makes it worth 2 points. Well, that's a bummer. We got a double question on there. But yeah, no, you're right, Jesse. Slope of 0. Let me email Terry and say this one is in the test bank twice. Thank you so much, everyone. This helps us out a ton too, and I can communicate with Terry. You liked my rubric idea? Yay! I emailed him earlier about the rubric. Statue 1, same 2, question showing up twice. Not a big deal. Big deal, but heard from a student they have this question twice. Worth 1 point. So it basically was worth 2 for them. There we go. Okay. Got that done right there. Only if I got it right. True. Yeah, I mean, but what does a slope of 0 mean? What does a slope of 0 look like? So what does a slope of 0 look like? What does a slope of 0 look like? I've graded interpretations. Can people see if I've graded? I haven't graded everyone's. Well, Sloan, you know what? Sloan, you want me to grade your interpretation? You're in here right now. I won't say grades or anything like that, but if you want, I could do that. Line is horizontal. Yep. So if I tell you this is your study time and this is your grade, what are you thinking with studying for this test? So what would you be thinking about with studying for Stat 201 if that's your study time and that's your grade? Yeah, I'll do it right here, right now. Thank you for being here. We'll probably end off in a little bit here. But what would you be thinking if that's study time and that's grade and the B1 is equal to 0, which is the coefficient of the slope? Now, the B0, which is this, is probably about 80. And that's B0. B0 here is not the important one.
It doesn't matter!
So what would you be thinking about this? How do I feel or how does Sloan feel? I feel pretty good about it. Like, I feel it went pretty well. I know a lot of students are discouraged. Test 2 is always the one. Test 2 is the one where test 1 is a lot easier because it's the general. Hey, Sloan right there. Here, I'll be working on. Sloan said he's fine with me grading it. I'm not gonna make any comments. I'm not gonna be like good or bad. I'm just gonna grade it, so you won't hear me saying anything. I will not be saying anything. Let me see here. 2 seconds. Gotta find a name. So gotta find the gradebook. There we go. Okay. So there might be some quiet right here. You can tell me if it shows that it's graded. I imagine it might. Okay. It only takes me about 30 seconds to a minute to grade these things. Okay, yeah. There we go. Right. I've updated score. So score is updated. Sloan, you don't have to say your grade or anything, but can you see your grade? Make sure I'm going to go off a different web page now because I was on the web page with it. Does it show the updated grade? Yeah, there's a lot of people who need to know there's 12 points still. Does it show I updated your grade? I'm not going to say. Yeah. If you want me to comment on it or like, I can't give you because this is great stuff. Yeah. I don't want to say anything good or bad. Does that make sense? But if you see your grade, you can react or not react. You said for me to grade it. It's just like you you have to say something. You have to be like, well, also I think about it nowadays. Like, what if it's not you, like someone faking being you? So now you can say your grade if you want, Sloan. I'll let you do that. It's you. So if you're the real Sloan, I'm just so afraid with like FERPA and stuff. Like, I want to make sure I do things properly. Yeah, nothing wrong with doing extra on your interpretations. You're free to say your grades. I think that's the best way rather than me saying grades. That way, if someone were to come in here and fake being someone, I am Robert Sloan Jacoby. Yeah, like what if someone made a fake account and I modded it, and then they were like, "Tell me my grades, tell me this," and then someone's like, "That wasn't me." That's why we have people communicate through their UTK account. But like, if you're here posting something and you know and you have access to it, then it's you. Or if someone broke into your account and did it, then that's on them. It's not on me for releasing information. So you are free to post your grades if you want. I should keep to that. You update on your side, yeah. And so I'm not gonna. I guess I can't even react. But if you want to, yeah, you probably know my reaction. But anyways, I'm gonna stop talking. But yeah, so I think the biggest thing to know. Go ahead and react. Yeah, great job right there, Sloan. Really proud right there. Go ahead and react as 91 exactly. Yeah, so really proud of you right there. This was a tougher test. So many people would be like, I wish I got in the 90s. Like, getting in the 90s is great. The tests are the toughest part of this class. They're the toughest part. If you even make B's on the test, you can make an A. So yeah. So that's what, yeah, let's go right there. 100 points in the chat. So we're gonna be talking today at the start of class about how to be successful. But you both said you did extra. I'm not gonna talk about what you wrote specifically, but it was clear to me, you mentioned your grade right here. That so people can assume what they want about your interpretations or whatever. But do you think, Sloan, that I made it very clear? And I'm not trying to put anyone down here, but were you very certain of what was going to be on the test? You're welcome, Sloan, anytime. were you very certain of like what those questions would be on the test? Now I'll be doing that for test 3 because we've already kind of covered that a little bit today earlier on about what to expect on test 3, and it was right over here and right down here. So check out the confidence interval part of the video earlier, where I went over I am blank % confident that the true blank is contained in interval blank to blank. And I did a full example basically covering today's lecture. So if you want kind of an example from the homework covering today's lecture, I do a full example going through the notation and kind of talking about what they're collecting data on right here. So you will be doing interpretations on test 3, and you have to know how to interpret it. And this is usually where the error is at. Like people usually know to put the confidence level, they usually know to put the values, but then they get really mixed up on what we're interpreting. But we're asking people, do you plan to move out of state? So we're trying to estimate the true proportion, because it's categorical, of people who plan to move out of state. A lot of people say true mean or true proportion, but you have to think, well, what are we asking them? We're asking them, do you plan to move out of state? Is it a yes, no question? So yeah, so a really good job, Jesse and Sloan, both of you. I'm not saying any grades wise, but like I think to me, it's about practice. You don't get these speed runs helped a lot. Understanding regression helped a lot with interpretation. I think I was nervous on the probability side. Yes, probability is tough. Probability is a big chapter. Like it looks small, but it's about just working multiple probability problems. If you look at the ones we were working, like a lot of the at least one problems. So here's where we're doing just different probability things right here. The probability of Burger King and McDonald's, and then knowing how to read the notes sheet right here, that it literally tells you the conditions, and then knowing the definitions of mutually exclusive, knowing the definitions of independent, knowing the definition of disjoint, which is mutually exclusive. That's where it's not about just working problems, which we always do. It's about knowing how to solve the problems and knowing the definitions of the words. So that's what we really focus on, like knowing complements add up. I also worry about the probability question. I really like that we did some of the yeah. And basically, I try to think of different ways of doing the questions. Like I think of different versions. I mean, it correlates to my Pearson's. Yeah, that's actually chapter 12. My Pearson questions are probably some of the most accurate ones to the test. Not that my Pearson's ever not accurate to the test, but if you look at what you do on my Pearson for chapter 12, then the test questions are pretty similar. It's probably one of the best chapters for like doing the My Pearson work and getting it down and knowing how to solve those problems will probably have you best prepared for the test. Usually I say Canvas content, but chapter 12 is a really good My Pearson one. Like made 100s on most of it, if not all the assignments from My Pearson, and really flex my exactly Sloan right there. And that's something I've shown. And look at this. We showed this earlier, but this is from another semester. It's aggregate data, so you're not seeing anyone's personal FERPA information or anything like that. But this is people's final score in the class predicted by how they did on the third quiz group, which are starting now. If somebody got a 0, if someone got a 0 on quiz group 3, they'd be predicted to make a 40 in the class. But for each additional point on quiz group 3, we would expect someone's grade to increase by 0.54 on average. Meaning, if you got 100, we would predict your grade to be about, now we're predicting it, it doesn't mean it is this, we'd predict your grade to be about a 94. That's the predicted grade. So we predict your grade to be this. And here's where we're getting into today, which is really cool. Now, what could we add to our prediction to give it an amount of uncertainty? Think ME. So I'm looking for the word here, ME, for 100 points. And this is kind of what we're end off, but I want to show this because this is so cool. What could we give somebody besides their predicted grade? We could give them a what or a sort of what for it. So what could we give somebody for their beyond just their predicted grade? What could we give someone? Ooh, look at those residuals. What could we give someone? Yeah, hashtag show up. Yes. Yes. Oh my gosh. Whoa. I'm showing this in class. We could give someone a confidence interval. So this is insane. I can't believe, is it 95%? No way is it that tight. That's on average. That's the true mean. Or it's for individuals. Is this not? This has to be. It's confidence over the true mean, right? The true mean of all students. Yeah, that's why it's so tight. I wish it was individuals. So I am 95% confident. I am 95% confident the average grade of a student in the class who gets 100 on my Pearson assignments is contained in the interval 93.1 to 95.5. And if you think about what I just did, I am using what we did earlier today and saying, I am 95% confident the true mean grade of students who get 100 on my Pearson 3, the true mean grade of their score, their final score in the class, is contained in the interval 93.1 to 95.5. And look where the most variation is. It's in students who are on the lower side. That's where we have the most uncertainty. You can also see it in the residuals that there's more scattered towards the lower end of grades, the people who have a lower predicted score, where there's a tighter cluster over here at the top, and then the residuals. What is the residual again? The residual is how much we miss by. So would you want to be this person right there, row 316? That's not a student ID or anything. That's just a row in a data set. Would you want to be row 316? Their residual is about negative 22, which means their grade was 22 points lower than it was predicted to be, because a zero residual means we got it right on. You wouldn't want to be that. That's not good. So it looks like we have a little bit of an issue of what towards the back of the plot over here. So the model's predicted power back here is a lot water, which we don't want. We want constant predicted power throughout the model. So that is an issue with the model, but I'll show you one last thing about it. It's a little heteroscedastic, right? Plot thickening, that's ish bad. That's not so good. What about this R squared right here? What do you notice about that R squared? 63% of the variation in your final score in the class is explained by quiz group 3. Quiz group 3, which is worth 6% of your grade, explains 63% of the variation in your grade. It is that powerful. It explains way over half. Like if someone told me I failed quiz group 3, I'd be like, ooh, that's not good. You could still pass, I'm sure, but it's a very strong explanatory variable of how somebody's doing in the class, even though it is only mathematically 6% of your grade. Something where 6% of your grade explains almost 2/3 of how you do in the class. If it explained 100%, I could know your quiz 3 group, like how you did, and then I'd be like, oh, you made a 98 because I know it. It would explain all the variation. So, yeah. So when people give up, and that's what drives me crazy, when people are like, I can't do it, I can't do these quizzes, I say, come to office hours. We'll do it. Just tell me which problem you're working on. As I was saying, do not let exam too good. Yeah, exactly. We still have a month. We still have material. When people give up, and I think that's partially what it is a lot of times people just give up and then their grade really suffers. And if you notice, there's also a little bit of nonlinearity at the bottom because the model should be going through the center of the data. It's just at the very bottom of the model, there's the nonlinearity because you can also see that in a residual plot. But yeah, so these are the things we want to analyze. We can actually see if there's a problem with the linearity of the model. Let me go look at that. Is there a problem with the linearity? We got to test for it. We got to test for everything. Here it is, lack of fit. Is there a problem? No, there's no problem with the linearity of the model. Lack of fit is to see if there's a lack of fit with the line, and the null hypothesis, the assumption we have is that there is not a lack of fit, and the alternative would be that there is a lack of fit of the line, like the line is a bad fit to the data, like when we fit a histogram and we assume that the normal curve is a good fit. That's actually a goodness of fit test, and you could call this a goodness of fit test for the line too to see if it is a good fit for the data. And since the p-value is high, we do not have evidence of a bad fit. That's not the significance of the model. The significance of the model is actually down here, which is actually the same as the the p-value for the F statistic, which interestingly enough, the F ratio right here is actually the T statistic squared. That's a fun fact. If you square the T, you get the F right there. Not enough decimals were carried though, so we didn't get the exact. Or you could take this and 559.6675 and square root it, and you get that T right there. Exam 3 will cover chapters we're covering instead of being comprehensive. There's what's called tools and techniques. Check out the review 3. Let's see if there's anything there. We'll end with that. So once again, make sure to be reviewing. Make sure to be going. The review videos, I hope they're posted. You might not have the review material posted because sometimes we update it. Here is review 3. Posted later date. Oh, these should load in. I don't know. Sometimes the page doesn't load everything. No. Well, if you want, watch this. You can cheat and see what's on there by going to the YouTube channel, and on the Stats One YouTube channel, embracing R in Python. What have you done, Hadley?
Working through the rebrand of our studio, broadening and embracing the.
I'm watching Hadley Wickham talk about. Sorry, I got very distracted. What's the deal with this, Hadley? Tell me about it.
That's my big message for the 100% believe in R. I think it is just a fantastic environment. Is some of the sort of like beautiful end-to-end orchestration that.
I don't want to get copyright claimed by him. I like R and Python, like. So wait.
Source products with all of our pro products that you try something.
Okay. I don't want to get copyright claimed by him. If I watch the whole thing, I'll get copyright claimed. Talk about the future posit. Excited for the future. Okay, there we go. Joey will be posting the data files for the extent. Yeah. Yeah, he's posting that right now. And then let's go. That way, if he copyright claims me, you can see he's like, oh, that was that dude watching my video. So go check out Hadley Wickham right there, Chief Data Scientist at Posit. It's now called Posit instead of R in our studio. Still getting used to that name change. Let's go to playlists. I'm very distracted today. YouTube, Stat 201, UTK. And so under the playlists, we got a lot of playlists right here, a bunch of hidden playlists for the classes and stuff. But if you go to like exam 3, test 3, there it is, test 3. Of course I call it different things. Ooh, this is a good one right here. I think, yeah, this, I don't think this says anything we won't be covering anymore. This concept review playlist is huge. So this Sloan right here is going to be one of your top playlists. This covers the 4 steps for hypothesis testing, 1 proportion z-test, t-test, 2 sample t-test, chi-squared. These are pretty much the remaining. We don't have confidence intervals in here, which I'll need to add. Yeah, exactly. Oh, wow. Yeah, go to the videos and just go to exam 3, right? So go to the search, go to exam 3. Will show up. Test 3 speed runs, exam 3 Kahoot. Watch out, the older you go, the less relevant it might be. Exam 3 review right there, and you can just see multiple reviews. Exam 2, so don't go to that one. But yeah, pretty crazy. I like my first Kahoot I ever did.
Is one report.
Go away, Brian. Stop that. I did for my old apartment. I was talking to my wife on the phone. Oh, is this the... That's what I did for my office. Wow, look at that. And I was being green screened? Why am I muted? Is it muted? The whole video muted? Why can't we hear me?
Audit.
Amazing.
We have a difference. Difference doesn't have context till we what it.
Look at the old
That's where-
Kahoot.
That's where.
Till we interpret it. Wow. When was this done? 2018. 2018. I think I brought the... Why am I being green screened? 4 years ago. Yep, this is the one. Looking
Hey
around.
everyone, it looks like we're live. I'm in the chat right
Look
now.
at me being like...
So hopefully the stream quality is working pretty well. It said it was bad to start, but if you are in the chat, go ahead and say hi. And let's hope the stream is working.
I hadn't streamed a whole lot. You looked at a lot of these reviews before exam day. It's all these memories of being like, oh, this is the one. Look at that. I've got like the streaming thing open right there. Yeah, that's the old YouTube stream thing right there. Amazing.
Okay, I think we're streaming the event.
I'm like, okay, I think it's working. Yeah, it's pretty interesting to see the whole YouTube progression right here. This is the one, right? Wow. Oh, those lamps.
All right, we might be streaming right now. Let's find out if you guys can see me and hear me.
4 years ago. Oh, there's me talking.
Hey everybody. How's
Hey,
everyone
everybody.
doing in the chat right now?
It's like I think the low def cameras make me look better.
It's so silent. Usually I have people in the room with me, and we're on a tiny bit of a delay.
There's been some Kahoots we did that had such a bad delay that it wouldn't even work. So I know, I'm just having some fun right here. Oh, this is the one. Look at all these old Kahoots. Like, I'm starting the stream and I'm like, is it starting? Is it starting?
Okay, I think you guys can hear.
The this is finally where we have it like real deal.
Yes.
Oh, that's the old music. This is our old music, which we got copyright claimed for. We had access to it, but this is the old intro music. So I just had to redo the video and redo the intro music. Oh, I better be careful. If we play that too long, we could get copyright claimed right here. I need to play that one. This is when we broadcast from the studio.
So you want to go to Kahoot. I've
I'd
got
be like
buttons.
leaning over, talking right there. But yeah, I gotta watch out. Hopefully that doesn't get this video. If this video has ads, it's because I got copyright claimed on that. Oh, and I used to go underneath the curve, but that got kind of awkward and I had to move myself around the screen. So it used to be the way I used to teach the 68, 95, 99. I would do this right here. It's because what I did in class. So I would mimic. I tell a lot of instructors what you do in class doesn't always work online. So it was better when I would annotate on the screen, but I was like live reducing my size and moving around the screen, and I don't think it worked as well, so I changed up what I was doing. And yeah, but yeah, well, awesome, everyone. You can see all the old school back in the day. I'm seeing if Julio Bourbon, that's Julio right there. Last thing to say, Julio Bourbon. Such an awesome guy right there. Oh man, that's such a cool Instagram photo. Let's go see. Here's Julio's. He is the nicest, like one of the nicest people I've ever met. Here is Julio Bourbon, former student, went to the played for Texas Rangers, went to the World Series. Awesome. Thank you so much, Sloan, right there. Yeah. I've been teaching online for since 2015 or so. So I've been teaching online for 7, 8 years. I did it before YouTube, and that's him and his wife. And Julio Bourbon right there. All the info on Julio. So we got some ads down below right there. There's his wins above replacement, at bats, but there he is in the chat right there, Julio Bourbon. Yeah, well, thank you, Jesse, right there. I appreciate it, and it's not just meeting people like Julio or anything like that, but Julio was just really. I got to meet him. He came to UT. And he does a lot to help out the UT baseball team, so he's a big supporter of the baseball team. But it's positive people. It's you, Jesse. It's you, Sloan, being positive. We want to help each other out, and I like doing it. I like teaching, and gosh, it seems like just yesterday Julio was in class. Like that was the start of the pandemic or whatever. So, anyways, with that, we'll be starting class here in about 34 minutes. Until then, Sloan, Jesse, great job. Keep up the great work. Tell everyone hard work pays off. We got this. And if hard work's not paying off, don't worry, it will pay off, because even if you don't do well on the tests, your homeworks, your quizzes, your data analytics, your Canvas contents are going to pull up your grade. So keep doing that work. Until next time, bye for now. Bye.